So, what was it? Thursday, we looked at classifying chemical reactions, and I listed out these 5 common reaction types that you're responsible for recognizing. So what you need to be able to do is to look at an equation that has all the elements or different elements or compounds mixed into it and match it to any one of these. Okay? And what we looked at Thursday as well was our combination reactions. We should, in theory, get through everything else today. There are a couple big ones that I think are a bit of a challenge, and that's going to be your single replacements. Is that actually going to work? Okay, it is working now. Our single replacements, I think, are a bit of a challenge, and to a lesser extent, the double replacements. But the single replacements tend to throw everybody for a loop when we get into the actual details behind those reactions. Okay, so just kind of be aware of that. You'll probably want to do a significant amount of practice. You're going to see a lot of practice show up in the activity that I'm going to make you go through and do. Okay, so keep this in mind when we go through and look at each of these different types. We started off with our combination, and we ended it with this last equation. Everybody went through and actually figured out what that last statement turned into, right? We turned that into an equation. Everybody did that? I know it's 8 in the morning, but everybody do that? Is that a yes or a no? Yes, everybody did that, really. So we don't need to show it up? Anybody need to see it? Not a couple people want to see it. Okay, that's what I'm looking for. Getting some hands up. So, started off with what we need to do is convert the statement or the words into symbols. Our first sequence of words is lithium metal. What symbol do we use? Li. And one of the things that we have to watch out for with our equations is we need to specify the phase. Li metal means what phase? Solid. So we're looking at the elemental species of lithium. Just put the parentheses and S. Sometimes you'll see that as a subscript, sometimes you'll see it as standard font size. The only reason it's really put up as a standard font size is so it becomes more obvious, but it's typically shown as a subscript. So we now have the first 2 words put in. Next part says it reacts. What does reacts mean? Plus. Just now adding it to something. Reacts with what? Bromine gas. What's our symbol for bromine? Br. Okay, and our phase is G for our gas. Okay, we have to be careful here. If we're looking at elemental bromine, we're not looking at a bromine atom, we're looking at the element of bromine. And what was special about the element of bromine? Have no fear of ice-cold beer. The beer is in reference to bromine. It is a diatomic molecule. You need the subscript 2. Okay, so bromine is diatomic in this equation. You have to include that. How would we know to not include it? We change the wording to lithium metal reacts with bromine atom. Okay, only under that circumstance would it be a single bromine. Okay? So, reacts with bromine gas to produce, and our to produce gives us that arrow. We now have to predict the product. Okay, based on the last statement there, what's our product going to be? Well, that's right. It's a combination reaction, so what do? We combine those 2 pieces into one thing. So we're going to end up with lithium and bromine. Before we get too into this, all we're going to do is take the element from one species and the element from the other, and we're just going to put them together. We're not concerned about how many there are of each of them. Okay, and we're also not going to be concerned about the phase in this case, because we don't expect you to be able to predict that. What we do expect you to be able to do is to predict the proper formula. So we've combined our pieces, which was just lithium and bromine, and now we want to look at that compound and say, is that formula balanced? How do we determine if the formula is balanced? We'll look at the charges. So when we take lithium and put it into a compound, it now becomes charged. What charge does it carry? A +1. When we take bromine and put it into a compound, what charge does it carry? A negative one. How did you know those charges? So number one, we could just straight up memorize it, or we pull from the periodic table. Lithium is in that first column. It is quickest for it to look like a noble gas by losing one electron. Where's bromine? Column 7. It is quickest for it to look like a noble gas by gaining an electron. So it's up to you how you want to deal with that, but you can use the periodic table to determine those charges. Okay? Now the question, is our formula balanced? The formula balanced. So I don't care about anything else, just lithium and bromine. +1, -1, formula's balanced. Now that my formula is balanced, I can go back to the equation and say, is my equation balanced? How do you know it's not balanced?
Because you have two bromines.
Right, so what you were able to do is inspect very quickly, and you looked at bromine, and on the right side, left side, side with the reactants. What is that? Left side. There are how many bromines? Two. How do you know there's two? The subscript applies to what's immediately in front of it. How many on the product side? 1. Does it balance? No. So what do we need to do? We need more bromine on the product side. So how can we make sure there are 2 bromine on the product side? We'll put a coefficient of 2. Okay? No subscripts, because what happens if we change the subscript? We change the formula. The formula is not allowed to change. You spent the time to balance it and make sure it worked. Don't touch it again. So we'll put the 2 in front of our lithium bromide. That 2 now applies to everything after it, okay, up to a plus sign. There isn't a plus sign, so it's just everything after it on our product side. So now when we look at our bromine, there's 2 bromines on the product side. What do we do now? Careful, we haven't even gotten to lithium yet. Check the lithium. How many lithiums on the reactant side? 1. How many on the product side? 2. Is it balanced? What do? We change the coefficient for our lithium and put a 2 in front, which means we now have 2 lithiums on our reactant side. Are our lithiums balanced? Yes. Now what do? Check it. How many bromines? Reactant and product. Lithiums. And now what do? Check it again. Okay? And check it again, and check it again. Right? If everything balanced out and you don't change a single number in any of those checks, then you're good to say the equation's balanced and you can move on. Yes?
You're going to take all this checking into account and put them together, right?
Yes and no. Okay. You can fully expect that you're not going to have 20 balancing questions because it does take time. Right? Right now what you should be doing is checking it to build the skill that you can confidently look at it and start to self-evaluate and not have to worry about checking it multiple times. So that when you get to the exam, how many times will you need to check it? Once. Okay? So take the time now to go through and check multiple times. In theory, by that 3rd or 4th time, you should be like, this is stupid. That's really what I'm trying to get out of you. Okay? I want you to say that this checking was ridiculously stupid. I don't need to do this. Because if you hit that point of, I don't need to do this, you're doing it right. Okay? Other questions? Okay. So there's our combination reactions. Next one is our decompositions. We end up with a variety of decomposition reactions. Sometimes we can predict the product, sometimes not. Kind of depends. So for this first example, heating mercury oxide produces, or sorry, let me say that appropriately. Heating mercury 2 oxide produces mercury metal and oxygen gas. So we've got our English. We now need to translate that into our symbols for chemistry. Let's take a second, have you guys write it out real quickly. just because I'm noticing organic students doing this, what should you write out for your problem? What's the first thing you should write down? Anybody? The symbols. At no point should you be writing heating solid mercury 2 oxide produces mercury metal and oxygen gas. Why should you not write that phrase?
I've never seen it again.
No.
It doesn't, it's not real.
If you're looking at your notes, you go back and look at your notes, you just see this equation that you write out. Right? How do you know what that equation is in reference to? Should be in reference to the question we asked in class, which was provide the equation for this. So why not write out that reference? I know, it's kind of an odd question. It has nothing to do with chemistry. It has to do with test-taking skills and note-taking skills. Do you have access to all of the PowerPoints? Yes. In those PowerPoints, is this written down? Yes. Why are you rewriting the question if you already know what the question is? Okay? Don't spend the time to write the stuff on the slides. What you need to be writing down is what we're adding to the slides. Okay? Just a general thought behind this. Now that you've had this soapbox lecture, let's go through and look at our answer. Because you guys were all not listening to me, right? And writing everything down. Heating solid mercury oxide. This is kind of going to be an interesting one to break down. Okay, where I would start is the solid mercury oxide. Where is that? Reactant or product? That's a reactant. How do we know that? Produces shows up after it. That's a nice way to look at it. Okay. Mercury oxide. So our symbol for mercury is Hg. Symbol for oxide, O. All right, what can we do now? What's that? We need to make sure our formula is balanced. We now actually have a formula that we've written down. We have to make sure our formula is correct. What is the charge on mercury? +2. How do you know that? Because I tell you it. That's what the Roman numerals meant. You didn't have to memorize it. What's the charge on the oxide? -2. How do you know that? You memorize that one. Okay. Net result, is our equation, or sorry, our formula balanced? Yep. So we can move forward. All right. So I'm going to skip heating for the moment. We're going to move to that word produces. What does produces mean? We've got our reaction arrow. Now we're going to double back to heating. How can I specify that heat was added to get this to occur?
The delta symbol.
If you remember back to all the symbols that we went through with our tables, we can put a delta symbol over our arrow or under our arrow, doesn't really matter, and that signifies that we are adding heat. Okay, now what do we do? Produces what? Mercury metal. What's our symbol for mercury? Hg. How do we know it's a metal? We specify that with our solid. Plus oxygen gas. Have no fear of. It's a diatomic molecule. It needs to be O2. Now that we've got all our symbols converted down, now we can worry about balancing. How do we go through and balance? Pick an element. Generally, pick Hg before we go with oxygen. Oxygen is one of the last ones we want to balance. How many mercuries do we have on the left? On the right? Is it balanced? Yep. Move to the next element. Oxygen on the left. Right? 2. Is it balanced? What do we do? We need a 2 over here to make the number of oxygens on the left side a 2. Is our oxygen now balanced? Yes. What do? Check it. So we go back to mercury. How many mercuries on the left? 2. Whoops. We changed a number. okay, which means we're going to have to check it again another 3 times. Okay, how many mercuries do we have on the right? 1. How do we fix it? We need a 2 in front of our mercury, and we end up with now our mercury balanced. Now what do we do? Check your oxygen. How many oxygens? 2 and how many mercuries? 2 and 2. Okay? We can continue to check until we go, oh, this is stupid, I should stop checking. Good job. We now have it balanced. Okay? Questions? Okay. I'll give you 2 minutes. Go ahead and work on this. So we've got a question and we've got an overall statement. Metal hydrogen carbonates will decompose to give a metal carbonate, water, and carbon dioxide. This one's a little bit trickier. We've got a lot of pieces coming out of this. So what does sodium hydrogen carbonate decompose into? Do we know anything about our equation? What are we starting with? Sodium hydrogen carbonate. And does it say I'm starting with anything else? No, so starting with nothing else. Sodium hydrogen carbonate. Is that sodium metal?
Yes.
If it's sodium metal, could it be bound to the hydrogen carbonate? No. In which case I would have said sodium metal plus hydrogen carbonate, or sodium metal and hydrogen carbonate, react to form. Is that what the statement says? No, it just says sodium hydrogen carbonate, which is the name of a single compound. Okay, so what we're starting with is sodium, symbol, Na, hydrogen, symbol, carbonate, symbol, CO3. We start with sodium hydrogen carbonate as a single compound. There's no ands or withs or anything like that to suggest any of those elements or any of those pieces are separated from each other at this point. All right? The other thing we could go through and do is remember that we're always dealing with neutral compounds. Hydrogen carbonate is a complex ion. A complex ion of what charge? -1. How do you know that? Memorized. Sodium has a charge of +1. Is our formula balanced? Yes. We now say that this compound decomposes. Okay, so that means we're doing a reaction. Do we say it decomposes with heat? No, so it technically should be with heat, but I got lazy and didn't write heat in there. Okay, so since I didn't add it, we won't add the delta symbol. What does it decompose into? Well, according to the statement above, metal hydrogen carbonates decompose. Right, well, sodium hydrogen carbonate. Is sodium a metal? Is hydrogen carbonate hydrogen carbonate? Should I say that again? Is hydrogen carbonate hydrogen carbonate? Yeah. Okay, so what we started with was a metal hydrogen carbonate. That's right here. What happens to those metal hydrogen carbonates? They result in the very first product, a metal carbonate. Okay? So what we're saying is that we take the metal and we combine it with our carbonate. So what metal did we start with? Sodium. And we react that or put that with our carbonate. What's the formula for our carbonate? CO3. Okay? To really emphasize the fact that we need to balance our formulas, let's balance the formula first before we continue on. What's the charge on carbonate? It's a -2. What's the charge on sodium? +1. Do our charges or does our formula balance? No. Because if we add those two together, we end up with a -1 overall charge. We need to balance that charge. How can we do that? We need 2 sodiums. Since we're looking at the formula, where can we put that 2? As a subscript. What happens if I put it as a coefficient? I'll have 2 carbonates as well as 2 sodiums, and my charges still won't balance. So we now have our proper formula. Now that we got the proper formula, move on to the next product. What's the next product? Water. What's our formula for water? How do I know H2O is not connected to sodium carbonate? I put a plus in between them. That's now saying my and, or in our paragraph or our sentence form, a comma. What's the last thing that happened? Carbon dioxide, CO2. How do I know the CO2 is not part of the water? Plus. Okay. Now that we've got our equation, we should attempt to go through and balance. Is it balanced? Okay, well, if we don't know, let's go ahead and check. Let's erase those charges. We'll start with sodium, just because sodium's fun to start with. How many sodiums do we have on the reactant side? 1 on the product side. 2. We need to balance it. What do we need to do? Put a 2 here. We now have 2 sodiums on the reactant and 2 sodiums on the product side. What element do we move to next? If we think back to what our rules said, we said pick any element other than hydrogen and oxygen. Okay, we should go with our carbon. How many carbons on the reactant side? How many carbons on the product side? 1, not 2. I lied. Let's try that again. Why is it 2? There's a carbon here and a carbon here. So it helps when you look at the whole equation, okay, as opposed to just pieces. So the number of carbons on the product side in total is 2. We don't care where it shows up. We just want to see how many there are on that side of the equation. So our carbon is balanced. We can move to our next element. Typically we jump to hydrogen. How many hydrogens on the reactant side? 2 on the product side. How many hydrogens? 2. Why is it 2? The subscript applies forward. Okay. Our last one is oxygen, which I'll move the slides down in just a second here. How many oxygens on the reactant side? 6 on the product side. That's all you get. Reactant side, you get 6. And on the product side, it's a little bit trickier because oxygen shows up where? Everywhere. So we have to make sure we count it in each of those positions. There are 3 oxygens from our sodium carbonate, plus 1 oxygen from our water, plus 2 oxygens from our CO2, and we end up with 6. Is our oxygen balance? Yes. So what do we do? Check it. Okay, you go back to sodium and go all the way through. Okay, and what we should find is that in theory we are now balanced. Questions about that? Slow, tedious process. When does it become faster and not so tedious? With practice. In all honesty, actually, it'll just become faster. It's still tedious. Okay? Next type of decomposition. I'll give you guys time to run through this one on your own again. Okay, calcium carbonate. We convert the words into what the symbols represent. So calcium is Ca, carbonate is CO3. Charge on carbonate is a -2, which you know because you memorized it. Right? Charge on calcium is +2. You can say you memorized it. That's starting to bug me actually a little bit. You can pull it off the periodic table. This is why we have the periodic table. Okay? So if you've got questions about determining charges on elements using the periodic table, let me know after class and I can walk through it with you again to make sure that you've got that. Because I personally think you've got limited space within your brain to have things memorized. The periodic table tells you the charge. Use the periodic table so you don't have to have that memorized. Okay? Our charge is balanced, so calcium carbonate is our correct formula. This then turns into our product. Okay? We get a metal oxide. What was our metal? Calcium. And oxide is... Oh, charge on oxygen? -2. And sorry, let me rephrase that because it's not a charge on oxygen, it's a charge on oxide. okay? Because oxygen would be the element. Okay, so in this case, it's the charge on oxide. Charge on calcium ion? Plus 2. Do our charges balance? Yep. So we can move forward to the next thing. What else is a product? CO2. Okay. Oh, that was dumb. I just told you what it was. Okay, what's the name for CO2 then? Carbon dioxide. Okay, so we name that according to its bond, which is a covalent bond. We can now go through and attempt to balance. We'd start with calcium, or carbon for that matter, it's not going to matter. Calciums, we end up with 1 and 1. Yep. Carbons, we have 1 and 1, which means we hope to God that oxygen better come out balanced. So what happens? Oxygen has 3 on the left, and on the right we have 3 as well. 1 coming from our calcium oxide, 2 coming from CO2. Gets us a total of 3. Went through that pretty fast. Everybody good with it? Yeah. Everybody think I'm going too slow? Oh, shucks. Could hope I was going too slow. Okay, we will slow down a little bit in this section. This section does get a bit dicey. Single replacement reactions. These are ones where you are required to predict products. Okay, so the previous two that we looked at are decompositions and our combinations. You're not required to predict those. You don't need to memorize anything off of those slides. We'll tell you what that information was. But didn't we just go through and predict what products were based on some given information? Yeah, we did. So when it gets to the homework, use that given information, either off the slides or from the textbook, to predict what products are. But when it comes to the exam, you are not required to predict the products of a combination or decomposition reaction. When it comes to the exam, you are expected to predict the products of a single replacement reaction. Okay? So our general format for our single replacement, we're taking some metal, we're reacting it with a compound, and in the process of that reaction, the metal ion from our compound is exchanged with the metal that we added into it. Okay, that's our overall balance with this. So if we take a look at the reaction shown, iron solid is mixed with aqueous copper 2 sulfate solution to produce what? Okay, this is an exceedingly tricky one, but unintentionally. So let's make it as simple as possible when you go through and do this. What are we going to expect to happen?
Iron sulfate.
We're going to expect to end up with iron sulfate and copper. Here's where we're going to run into some questions here. What is the charge on the iron? We don't know that one. Okay, so to go through and balance this one, it's very hard to balance that, because iron has multiple possible charges. It could be iron 2, in which case is our formula balanced? What's the charge on sulfate? -2. Our charge on iron, which we just said, if it was iron 2, it's +2. Our formula is balanced. If iron was iron 3, is our formula balanced? No. Okay, so that makes things a bit dicey. Because of that, we'll just keep it simple. We'll assume we're going to iron +2 for the sake of this question. Okay? Next part of this. What charge is on the copper that's produced? Okay, this is trickier. This is one of our issues that pops up with our single replacement reactions and that we don't clearly see in our single replacement general form. What was the charge on the iron solid? Right in the reactant species, right here. What's its charge? Where is the charge specified in a formula? Always. Every single time. Upper right-hand corner. What is in the upper right-hand corner of FeS? Nothing. What is the charge on the iron solid? 0. There is no charge. Because if there was a charge, it would be specified in that upper right-hand corner. There is nothing there, which means the charge in the iron to start with is 0. Okay, what happened to the iron in the course of this reaction? It started at a 0 state and it went to +2. seems a bit odd. How could it do that? It had to lose 2 electrons. Okay, why lose? What's the mathematical symbol for loss? Subtraction. What's the charge on an electron? Or sorry, how many electrons did it lose? 2. What's the charge on an electron? The net result is what charge? Positive 2. There's where our plus 2 came from. It's a loss of 2 electrons. Remember I said you got to watch out for that minus sign. Nobody believed me. Oh, minus signs aren't that big of a deal. Guess what? Understanding that that minus sign means subtraction, or that means loss, we can now determine the charge, potentially, for our iron. Okay, or see what happened in the course of that reaction. Where did those 2 electrons go? Because I don't see anything in there that says where the electrons went. Copper accepted those 2 electrons. What charge did copper start as? A plus 2. If it now has to take the electrons, what mathematical symbol are we looking at? A plus. It's adding how many electrons? 2. What's the charge on an electron? Negative 1, which equals? 0. What's the charge on the copper in the product? 0. It has no charge. So when we're looking at the single replacement reaction, we take an element in it, or a metal in its elemental state, and we swap it out for a metal ion. In the process, the metal ion that comes out goes to its elemental state. Okay, yes, it's a little bit tricky. We'll look at some of the aspects of what's happening with those electron transfers in a little bit. Okay? Questions about this? Really, nothing? You're just hoping I'm going to give you more information in a second? Okay, there we go. A little more brave.
So the copper has a 0 charge?
The copper has a 0 charge in the product.
It means the sulfate attached to it has to have a 0 charge as well? Might be balanced.
Is the sulfate attached to our copper in the product?
Oh, okay.
No. So we don't worry about the sulfate. The sulfate is what's hitting to our iron, and as long as we know our iron's a plus 2, that's balanced.
Okay, so I'm sorry, I misunderstood the reactants. Had the copper in the reactant.
Yep. What was the charge on the copper in the reactant? Had to be a plus 2 because the sulfate is minus 2. So our copper has to be a plus 2. Yeah? The only way you would show it is by looking at the products, okay, and then balancing the equation. Okay, so that's how you would have to bring in your understanding of what those charges were. I happen to pick a poor example for this first one because both copper and iron are ones you don't know the charges are on. Okay? So the next question is, does this reaction occur? That's a tricky one. Okay? What we're saying in the course of this reaction is that iron is more reactive than copper. Okay, why are we suggesting that?
Because it kicked copper out of it.
It kicked copper out. Iron is more active. It goes around and deals with more compounds than copper does. So now given the choice, okay, we're going to see iron sit with our compound, not the copper. Okay, we could look at it as a, no, I don't want to do that. That gets kind of slippery slope. At least not while being recorded. Here we go. Let's fix that. How we gotten out of that kind of potentially gross analogy. How do we know iron is more active? Okay, and I heard someone mention electronegativity. Are you required to know the electronegativity of any of the elements? No. We're required to know a trend. The more electronegative is in the upper right-hand corner. So we could try and make some parallels with electronegativity, and we'll find out very quickly that doesn't work very well. Okay? So how do we know? We know because somebody, a long, long time ago, ran this reaction and saw that a reaction occurred. Somebody a long, long time ago took a different metal, put it in the same situation, and noticed, did a reaction occur? Oh, no. Well, if it didn't occur, then that means the activity is the other direction. Okay? And they took all of that data and they compiled it into a table. And then with that table is how you answer the question. Makes it interesting for the exam. For the exam, how would you be able to predict what happened with your product?
Provide us the table.
I could provide you with the table, or the other option is
Yes.
you have the table memorized. Oh, thankfully we aren't doing that. I will give you a table. All right? So when you go through and do your homework, realize you have a table, use it. All right? That table is in your textbook. You can find it online. You can also find it on the slides here. Depending on what elements we're particularly concerned about, you may see more or less metals within your table. So this is a shortened version, because officially we can look at all the metals on the periodic table. So you're looking probably 50 elements. Right? This does not have 50 elements. So if we take this back to, let's see if I can do this slowly. Yeah, cool. If we take this back to our equation, we said iron was more active than copper because it wanted to be with a partner. Let's take a look at our table. Where is iron on the table?
About halfway down.
About halfway down. Notice we made it a little bit more difficult. We wrote it out. There's our iron. Where's our copper?
Further down.
Further down. Which of those two elements is more active according to this table? Iron. Which means, what do we expect to happen with this reaction? Iron will kick out the copper. Okay, so we're using this table to go through and predict the reaction. The first thing that I would go through and do is ignore the table and draw out your equation. Do the exchange so that you can then compare and see what it looks like. Once the equation's actually drawn out, then you can go through and interpret according to the table. Okay? Again, it's going to depend on what question's asked. Okay, but ideally you should go through and balance first. Okay, so let's take a look at a couple examples. Should we do one more together before I send you off on the rest?
Sure.
Okay, so let's take a look at this next equation. What are we reacting? What's going to happen for our double replacement? This one is a little bit trickier. What's metal number 1? Iron. What's metal number 2? Chlorine's not a metal. And hydrogen's not a metal. Oh, I give up. Let's go home. No, okay. Where is hydrogen on our periodic table? Upper left. Where are most metallic elements? The left side of the periodic table. Hydrogen may officially be a nonmetal, but chemically it acts like a metal. Right, so when we're looking at our double replacement reaction, hydrogen is our metal in this circumstance. So let's go through and run our reaction. Oh, it looks like I even gave you some hints as to balancing. Okay. We're going to exchange the iron for our hydrogen to end up with iron chloride. The element left over will be hydrogen. Is that formula balanced? How do you know that hydrogen formula is not balanced? Have no fear of ice cold beer. It's a diatomic element. We need the H2. Okay. Again, trying to go through and balance the iron chloride is going to be a bit difficult unless we knew some more information about these species. I did kind of sneaky backhanded tell you that we have to have a 2 here. Okay. So what does that mean? How many chlorides do we need to show up in our product? 2. More than likely, we're looking at Cl2 here. So it's FeCl2. I would not expect you to predict that. What we're looking at is just kind of coming up with this as best we can. So when it comes to charges, don't worry about the charges unless it's something that you are required to know. If you're not required to know the charge, for instance, with all of these stupid examples, they're my examples, so it's really my stupidity. Gold, we don't know the charge on. Gold, we still don't. Copper, we still don't. So go through, just swap it out with the ions. Don't worry about balancing the equations, but predict, does a reaction occur or does it not occur? So in the case of our iron with acid, we'd go to our table and say, we have iron here, and we have our hydrogen here. Which one is more active, iron or hydrogen? Iron. What does that mean? Iron wants to be with a compound or with another element more than hydrogen does. So when we add iron metal to HCl, what happens? It replaces. This is an example of a single replacement reaction working. Okay, just like the previous one. So go through and work with the next two, see what you can come up with. Neither reaction works. Okay, so if we took a look at just kind of guessing at this, we'd expect, as a general formula, gold to come across, react with our sulfate, and we'd end up with hydrogen gas. In the other case, we'd end up with gold, sulfate, with copper left over. So we can now take this information back to our table and look at where gold is relative to hydrogen. Where's gold relative to hydrogen? It's lower on our periodic table, or that's not periodic table, our activity series, which means which element would rather be with a compound or be in a compound? Hydrogen. Where is hydrogen in a compound? In the reactant, it starts in the compound, which means the overall reaction in this case is no reaction for that first one, or that third example. What happens when we take gold and we put it in with copper sulfate? We find where gold is and where copper is. Which one's higher in activity? Copper, which means copper prefers to be with a compound or prefers to be in a compound. Where is copper in a compound in our equation? It's in the reactant side, which means no reaction. Sorry, N comes before R. No reaction. Does that make sense? It's kind of an interesting question. Does it make sense for gold to have no reactivity? What's our most valuable mineral? Gold. Why? It doesn't react or break down with anything. Imagine if we pick something on the opposite end of the spectrum, lithium as our currency. Okay, we try and pass lithium around, okay, as our monetary value. Okay, someone decides they don't like your source of lithium, so they go, you know what? I'm going to destroy all of your national wealth. What do they walk into the vault with? Water. And get a little squirt gun and they just start squirting the lithium. What happens to the lithium? It reacts very violently and explodes. And it does what to all of your lithium? Blows it up. All of your monetary value has now gone up in a big poof of violent flames and nastiness. Okay? Gold is picked as our monetary value because it does not react with other things. Which means if some thief comes in, busts into our vaults of gold, they can't sprinkle water on it and have our value all of a sudden disappear. They have to try and pick it up and run with it. Okay? That's a lot of effort. Okay? So gold is very low in activity, and that's why it is one of our primary precious metals. Okay? Because it doesn't react with anything else. Okay? Which also means chemically it is completely useless. So if we look at it from a chemical perspective, is gold really all that valuable? No, because I can't do anything with it. Once I've got gold, I'm stuck with gold. All right? So we typically look at other materials having a lot more value to a chemist because we can do something with them. All right? What are the other precious metals that you're aware of? Lead? Oh, palladium, which isn't on this chart, so pick another one. Platinum, our other common one. Where are they on our activity series? Also, right at the very bottom. They have very minimal chemistry available to them, which is one of the reasons why we use them as our precious metals and as our form of monetary currency. Okay? Kind of a fun statement out of that. So on the exam, the upper right-hand corner just popped up. I will give you a condensed activity series. So you are responsible for reading that series and deciding does the reaction occur or not. Okay? So last thing that we'll look at before we move into chapter 17 actually is this idea of active metals. There are certain metals that will do a replacement reaction, officially a single replacement reaction with water. Okay. What's the metal in the case of water? It's still hydrogen. Okay. It's a little bit of a special case because the hydrogen in water is actually relatively stabilized and it's not acting truly as a metal. When we go back and look at both HCl and our H2SO4, the hydrogen in both those cases does act very chemically like water. Okay? Those hydrogens are formally positive and very, very reactive. In water, the hydrogen isn't quite as positive. If it's not quite as positive, it's not quite as reactive as a metal, and only certain metals are so much higher in reactivity that they will do the single replacement reaction with hydrogen from water. Okay? Those are known as your active metals. Group 1 metals are all active metals. Okay? There's several within Group 2 that do the same thing. All right? This is why if you take one of those metals and you throw them into water, you usually get this big explosive mess. Feel free to YouTube some videos on that. I probably should have YouTubed one so you can find it or so you can see it. Okay? But as we move down the periodic table, so we add lithium to metal, we get this, or lithium to water, we get this kind of violent flaming reaction. If we move all the way down to cesium, we throw it into water, it actually blows up the entire system. Okay? Container holding the water, the blast shield, everything. It just kind of really, really, really reacts. Okay? So there are these things known as active metals. That's about all you really need to know out of it. I won't directly test you on those because the hydrogen in the water is kind of a rare exception. It's just that those metals are so active that it allows for the reaction to occur. Okay? So, chapter 17. We're looking at, it's probably going to be 17.1 through 17.2. I want you to, because I think 17.3 is the balancing section of chapter 17. You should avoid that section like the plague. Okay? Because the textbook goes through horrible, horrible reactions for balancing these types of conditions, our redox reactions. Okay? So focus more on examples that we talk about in class. You might see one example on the exam. What you will see is, to a larger extent, is the aspects that we're going to talk about. Okay? So, we look at this reaction. What type of reaction is this? Fair enough. It is an oxidation reduction reaction, or a reduction in oxidation reaction, also known as redox. But that's not one of the 5 types I told you to recognize. This falls under one of those 5 types. It may help you if I rewrite H2O as HOH. It's not officially a double replacement either. No, I don't even want to look at neutralization. As a hint, we just looked at this type of reaction. It's a single replacement. We're swapping our calcium ion for hydrogen. The net result is that we end up with hydrogen in its elemental state and calcium in a compound with the OH. Okay? So we have a single replacement type reaction. Okay? What's the charge on the calcium in the reactant? Where do we find the charge? No. Where do you find the charge? Upper right-hand corner. What's the upper right-hand corner for calcium solids show? Nothing, which means the charge on calcium in that state is 0. What is the charge on calcium in our product? This is a little bit trickier. We can look at the upper right-hand corner, and our overall charge is 0, but that's the charge of that molecule, that whole thing. What's the charge on just the calcium? Two ways to answer this. +2, which is going to be the answer. Why is it +2? Periodic table, number one answer, because our calcium always holds the same charge. Right? The other issue, hydroxide has what charge? -1. How many hydroxides are there? 2. So to balance, calcium needs to be +2. What happened in the course of this reaction to go from calcium 0 to calcium +2? It had to lose 2 electrons. So if we look at this as a reaction, where would I put those 2 electrons? On the reactant side or the product side? Okay. Let's say we lose 2 electrons, and we put those 2 electrons on the reactant side. What's the charge of 2 electrons? -2. What's the charge on calcium? We already said was 0. +2. We cannot create or destroy matter, so our overall charge on our reactant side, being -2, needs to equal charge on the product side. +2. Does it equal? No. Did we put the electrons on the right side of our reaction? Or the correct side? No. If we're going to lose 2 electrons, whoops, that should be an eraser. If we lose 2 electrons, where do we put the electrons? On our product side. We can only ever add electrons in a reaction. Okay? So we say species A plus species B gives us species C. We never say A minus species B gives us species C. It doesn't happen. So the same thing is going to happen when we look at our equation. When we're looking at our electrons, if we lose 2 electrons, that means our electrons came out on the product side. What happened to our hydrogen? What charge did it start at in our reactant? It's a harder question. It's the charge on the oxygen. -2. What's the charge on our hydrogen have to be to balance out that -2? Has to be an overall +2, but why is it +1? There's 2 hydrogens. So the charge on our hydrogen to begin with is a +1. What did it go to? Whoops. What did it go to over here? A 0 charge. What had to happen to go from a +1 to a 0? It had to gain a single electron to balance out that charge. So we could add 1 electron over here. When we do the math, we get that 0 charge. So what we're looking at in the single replacement reaction is an exchange of electrons. Electrons went from one atom and then were dumped on a different atom. Calcium gave up 2 electrons. Those 2 electrons were absorbed by hydrogen, allowing it to convert, or hydrogen ion, allowing it to convert into hydrogen gas. This transfer of electrons is what's known as reduction and oxidation. Okay? If we look at our blue circumstance, that was a loss of electrons. That loss of electrons is referred to as oxidation. The gain of electrons for our hydrogen is referred to as reduction. Okay? So when we talk about our reactions, almost always you'll hear them referred to as redox reactions. Okay? And that's because if we do a reduction, we have to do an oxidation. They come together. Why? Well, have you ever seen an electron in an equation? No? Why not? They are ridiculously unstable. Think about sticking your finger in the electrical outlet. That's really an unpleasant experience. Okay, that's because the electrical outlet has a bunch of electrons in it and ready to fire out. Okay, so we've put them at that higher energy state so that we can take advantage of it to power our lights. Okay, if we stick our finger in it, we're now pushing those electrons into our body, and that's really, really unpleasant. Don't ever stick your finger in the electrical outlet. Okay, just in case, I got liability reasons. Okay, I'm not recommending you do that. Okay? Again? Yeah. So we're looking at this redox process. So we want to come up with ways to find out what's happening within this. And it also means we end up changing some terms that happen within this. We're going to come up with something known as an oxidation state. The oxidation state or number, I'll bounce back and forth between those two, will always refer to an atom. Always. So if I ask for the oxidation state of hydroxide, that's an invalid question because hydroxide is not an element. Okay, oxidation state always applies to an atom. Charge, on the other hand, applies to a molecule. Okay, but our molecule term is too open. So what we'll do is change it into a unit. When we look at an equation gives us the reaction of units with each other. If I want to determine the oxidation state, I have to answer the question slightly differently. And it is very confusing between these two because in certain circumstances, the charge happens to equal the oxidation state. Okay? But they are different things. The oxidation state implies some characteristic of the atom. The charge implies a characteristic of the unit, or whatever is reacting. Okay, so oxidation number or state rules. You do need to know these rules to go through and determine your oxidation states appropriately. So any atom in its elemental state has an oxidation state of 0. Okay, nice simple rule. Any monatomic ion, the oxidation state equals the number or equals the charge on the ion. Okay, after that, we start to move into some gray areas. Nonmetals are usually negative, but there are some pretty massive exceptions to that. Okay? So in general, what I would do is ignore that first statement and really focus on the rest of these rules. Oxygen will have a -2 oxidation state. Always. Ish. 99% of the time. Okay? Hydrogen will always carry a +1 state unless it is bound to a metal. When it's bound to a metal, it changes its oxidation state, becomes -1. You won't ever see that, I don't think, so we won't worry too much about it. And then your halides, so fluorine, chlorine, bromine, and iodine, will be -1 in all cases except when bound to oxygen. So we have kind of an order of priority in these. Oxygen, -2, always. It trumps everything. Hydrogen, almost always a +1, so we can get away with most circumstances saying it's a +1. Halogens will be -1, except when Rule 3a butts in. Okay? Last thing, very, very familiar. It's pretty much the same equation we use to balance out formulas. We're looking at the sum of the oxidation numbers equaling the charge on the molecule. All right, how do we know what the charge is on the molecule? Where is charge always specified? Upper right-hand corner. You are always given the charge. You are never given the oxidation state. Okay? So let's go ahead and take a look at, let's actually see. Sure, let's push it one here. Calcium in our reactant. What's its charge? 0. Okay? According to Rule 1, we could go through and say its elemental state is, since it's in its elemental state, its oxidation state is 0. I'd switch that up. Look at Rule 4. The sum of the oxidation numbers equals the charge on the molecule. What did we say the charge was on calcium? 0. Well, how many calciums are there in this formula? Just 1. What's its oxidation state have to be? 0. Straight from our equation. Okay, just adding up the oxidation states of all our elements. If we don't know the oxidation state of calcium, it's X. There's only one X, and I know that has to equal 0, which means X equals 0. How about hydrogen in our product side? Okay, what's the charge? How do you know it's 0? Nothing written in the upper right-hand corner. How many hydrogens are there? 2. Do we know its oxidation state? So we run under the assumption that you always must calculate the oxidation state. It's X. What does X have to equal? 0. What's the oxidation state for hydrogen in H2? 0. The charge is the oxidation state. How about in the case of water? What's the charge, or the oxidation state, sorry, of hydrogen in water? Okay, we could cheat and go off our rules, or we could remember just rule number 3A. 3A says the oxidation state of oxygen is -2. Okay? How many hydrogens do we have? 2. We assume I don't know the oxidation state. This has to equal the overall charge on water, which is 0. What does X have to be? +1. Hallelujah. Matches 3B. The equation will always get you the answer. Okay? So when it comes to determining oxidation states, you really just have to remember one thing. The sum of the oxidation state, well, 2 things. Sum of the oxidation states equals your overall charge. The next thing, oxygen has a -2 oxidation state. The rest of it is stuff you've already got memorized when you went through and did your nomenclature. So, if we take a look at these formulas, what is the charge for that first structure? It's the charge for the second structure. +2. Charge for NO3 or nitrate. -1. The charge on sulfate. -2. Charge is given to you. It's in the upper right-hand corner for every single one. Where it becomes challenging is when we now go through and look at the oxidation states. What is the oxidation state for our copper? 0. Cool. It's the same thing as our charge. What's the oxidation state for the next one? How much? Whoa, that jumped way too fast. The next one, +2. Now we get a little bit trickier. What's the next one? I need to ask the proper question. Oxidation state is per element. So what's the oxidation state for oxygen in nitrate? Rule 3A. Oxygen has what oxidation state? -2. What's the oxidation state for nitrogen? So this is where a lot of people say, well, -3. -3 is the charge on nitrogen in an ionic bond. This is not an ionic bond. So what we would need to go through and do is use that formula. The sum of our oxidation states equals the overall charge. We don't know the charge on nitrogen, so let's call it X, plus the charge on oxygen. -2. How many oxygens are there? 3. So I could go through and write out all the way through just because it's nice and tedious and might as well do it. Fill up the last few seconds of class. This has to equal what?
-1.
Why did you say -1? Because it has to equal the overall charge. So 0 was our overall charge when we dealt with nomenclature, because we said everything had to be balanced at 0. That's when we're looking at charge. Are we looking at charge anymore? We're dealing with oxidation states. That has to equal the overall charge on whatever we're looking at. What's the overall charge on nitrate? -1. How do you know that? Upper right-hand corner. When you go through and now solve for X, you find that X is equal to +5. What? That has nothing to do with the -3, and rightly so, because the -3 is the charge. +5 is the oxidation state. Okay? Please go through, test this on your own with the sulfate. You should be able to get +6. We will pick up with the next slide, which looks at defining what's happening within reactions on Thursday.